Welcome to Robo's Physics Adventures. Today Robo is going to discover how to convert motion diagrams into position time graphs. Students are continuing to work on the data that was collected from the 2019 Ironman competition. Mr. S was able to get more detailed motion data about 15-minute swim of one of the athletes. The time interval between the recorded dots is 1 minute and the reference point is at the start of the race. Mr. S asks students to describe the motion. Robo is grouped with Dennis and Jackie today. The group discusses that since the motion is not starting from the reference point, it means that the data corresponds to a time after the race has started. Dennis says that the swimmer seems to have a constant speed at the beginning and the end because the spacing between the dots are pretty consistent in those regions. Robo says that the spacing between the dots gets smaller in a certain region and then bigger again. Very likely the swimmer had to stop, maybe to adjust their swimming goggles or to take a short rest. Jackie says that there is no indication of start and end point here. Should we assume that the swimmer is swimming away from the reference point or towards it? What if the swimmer realized that they had forgotten something and were going back to retrieve it? Mr. S said that these are fantastic ideas. It is very important to show the start and the end events using numbers or words. In this particular case, let's assume that the swimmer is swimming away from the reference point. Mr. S used this opportunity to teach students about converting motion diagrams into a position time graph. He said, as we discussed previously, the position is how far the object is from a reference point and in what direction. In this situation, the positive direction is chosen to be the east for our sign convention. We will sketch the position time graph here without any numbers. In a position time graph, the time or the horizontal axis represents the reference point. We will assume that the first data point has been recorded at time 0. Since this point is in the east of our reference point, based on our sign convention, it's positive distance away. We will plot this position at time 0. We know that the time between every dot is 1 minute. Therefore, 1 minute later, the object has moved further in the east direction. We will plot that, and then we will continue to do this until we have plotted all of the 15 points. Once we have all the points plotted, we will use the line of best fit to connect them. The line of best fit will help us find the trend of the pattern. This line is either a continuous straight line or a curved line. Note that any calculation made from a graph should be based on the line of best fit and not any individual data points. The students were asked to sketch the position time graph for the same graph, where the runners were traveling in different directions. Robo's group followed the procedure. They started by seeing how far the dots were from the reference point and translating that into the position axis of the graph at different times. They've noticed that the position time graph for a constant speed will result in a straight line for the position time graph. In the first graph, they also noticed that the runner was moving away from the reference point in the direction of east. In the second graph, the group noticed that the runner was running at a constant speed towards the reference point in the west direction. In the next set of graphs, there were dots in the non-positive portion of the motion diagram. The students followed the same procedures. They found that the runner was running towards the reference point at first, then reached it, and then moved away from it. The runner ran in the east direction throughout and at a constant speed since the line of best fit was a straight line. The same idea applied for the second graph, but the only difference was that the runner was running in the west direction. Mr. S added that all of the positions to the left of the reference point could be either considered as a positive west direction or negative east direction. Also, note that when the gradient or the slope of the line is positive, the object is moving towards the positive sign convention, in this case east. When the gradient or the slope is negative, the object moves in the opposite direction of the positive sign convention, in this case west. In the next set of graphs, the students noticed that one of the runners was running at a faster speed compared to the other. After graphing both situations, students noticed that the graph that had a steeper gradient or slope was the faster one. Dennis said that this makes sense because if the object isn't moving much, the position will not change much, and therefore the gradient or slope of the line will be horizontal and close to zero. As they move faster, there is more change in the position, and this would increase the gradient in the position time graph. Mr. S added that the magnitude or the positive value of the slope in the position time graph is representative of the speed of the object. As we explored, the sign, whether it's positive or negative, is representative of the direction that the object is moving. The next set of graphs were of two runners that were speeding up and slowing down. The students plotted both of the graphs. Jackie noticed that the spacing between the dots in the first motion diagram was increasing, indicating that the runner was speeding up. The vertical distance of the dots in the position time graph was also increasing as a result. Jackie looked at the gradient or slope of the line and realized that it was also getting steeper. Since the steepness of the gradient or the slope is the indication of the speed of the runner, this made sense that they were speeding up. Mr. S added the idea of a tangent. In general, a tangent is a straight line that touches a curve at a single point and represents the gradient or slope of a curve at that particular point. We can see that the steepness of the tangents for the curve for the position time graph are increasing. Jackie said, in the second graph, the spacing between the dots are getting smaller, indicating that the runner was slowing down. I'm noticing that the gradient or the slope of the tangents for the line of best fit are also decreasing in steepness with time, and this is consistent with the idea that the speed is decreasing or that the runner is slowing down. Mr. S used this opportunity to do a bit of review and to introduce the concept of displacement. He said, as a reminder, the position is how far the object is from a reference point and in which direction. We use the letter D with an arrowhead to represent position. The arrow on top represents what we call a vector quantity. A vector quantity has both a size, which indicates how big or small it is, and a direction that helps us know the direction with respect to the reference point. Geometrically, a vector is an arrow that connects the start position to the end position. The vectors for all the positions are shown using gray in the motion diagram. Note that all positions start at the reference point, which is the tail of the arrow, and end at their event, which is the head of the arrow. Assuming that event 1 starts at time 0 and that all the dots are recorded every 1 second, the position time graph is shown. Note that at each time, the appropriate vector shows the position of the object on the position time graph. The change in time between two events is represented by a triangular sign of delta, which means change, and a lowercase t, which stands for time. For example, the change in time between events 1 and 3 will equal to the time at which event 3 takes place minus the time at which event 1 takes place. The final concept for today is displacement. Displacement is the change in position, and we use delta D with an arrowhead indicating that displacement is a vector quantity with a size and a direction. The displacement from event 4 to 5 is the change in position from event 4 to 5, or position 5 minus position 4. The geometric subtraction of the vector is shown in both the position time and the motion diagram. We will explore these ideas further later. For now, let's use the position time graph of one of the athletes in the triathlon to describe her motion. Robo said, "It seems like this is very representative of the three sports. We can break down the graph into 3 intervals for these sports. For the first section, the line is quite straight, meaning that the athlete was swimming at a constant speed. Since the slope is positive, it means she was traveling in the direction of the positive sign convention, which in our case is east. Since the steepness of the gradient or the slope is low, it means that she was swimming at a relatively slow speed compared to her bicycle ride and the run. As the athlete is transitioning between the sports, the slope increases, meaning that she is speeding up. Dennis said that during the bicycle ride, the line is almost straight, meaning that she has a constant speed. The gradient or the slope is positive, meaning that she is moving east, and the steepness is high, meaning that she is traveling fast. During the transition to running, the steepness of the slope is decreasing, meaning that she is slowing down. Jackie said that during the run, the line is almost straight, meaning a constant speed. The gradient or slope is positive, meaning that she is traveling to the east. The steepness is medium, meaning a medium speed compared to swim and the bike ride. This ended up the lesson for today. Robo had lots of concepts to review. Robo had learned about translating motion diagrams into position time graphs. It had also learned about how to use position time graph to describe a motion of an object based on the shape of the curve and the slope of the line. Robo had also learned about the concepts of tangents, positions, and displacement. Robo will be reviewing the concepts later in order to make more connections in its circuit so that it can recall the information better. Robo is looking forward to learning more about these ideas in the future.